What is the ideal banking angle for a turn in a road at a speed of 30 meters per second, given that the turn has a radius of curvature of 120 meters? Well, it looks like I forgot to put a question mark there, but fortunately this is not an English class or a punctuation class, so I assume there's a question mark there, right? Speaking of language, let's talk about what does ideal banking angle mean. The definition of ideal banking angle is that is the angle of a turn with a given radius of curvature and for a given speed at which no traction, in other words, no friction force at all, would be required for a vehicle to safely make it through that turn. So in other words, like if I draw kind of a picture here, I'm going to draw similar to some previous examples. I'm going to assume that I'm taking kind of like a back view of some vehicle here. I'm just going to let some sort of like pseudo box represent my vehicle here. Put a couple like tires on it or whatever. Tires with wheels in them presumably, but make that a little bit wider. Okay. There it is. That's good enough for me. And again, we're assuming a back view here. Maybe it's making a right turn. That's what that direction of banking seems to suggest. I'm going to go ahead and throw in for this one already that I think the direction of acceleration is horizontal and to the right. But when I start to do the free body diagram, ordinarily, if this were not an ideal banking angle situation, I would have three forces. I would have gravity force, normal force, and a traction, or as we commonly call it in physics, a static friction force. But in an ideal banking angle situation, there will be no static friction force, no traction required, in other words. So that means my free body diagram can be, make that a bit more of a G, simpler. All I need are the two forces, the force of gravity and the normal force that I've drawn here in a relatively small kind of way. So let's go ahead and to answer this question, since we're just looking for that ideal banking angle, I'm going to analyze this with Newton's second law. That's probably one of our most useful formulas right there. So far, at least in this class. We're going to explore some other methods in a chapter or two more. Anyways, but in this case, we're just going to have force of gravity plus normal force. I always pause for a second because I'm kind of like, do I want to do this one first or the other one first? And it really doesn't matter, but sometimes aesthetically it might matter a tiny bit. But maybe I shouldn't let that bother me, right? You shouldn't let that bother you either, which one comes first, I guess, but we're all humans. Things happen. I'm inclined to do a components analysis for this situation. I think a geometric analysis might be possible. Things are reasonably simple, and there are some right angles there, but it's maybe not the most convenient thing to do, and I'd probably have to maybe subtract the MA from both sides. Things get kind of weird if you do that. So hence I prefer a component analysis for that, and for this, that is. And for the X component, I'm going to write the following, and maybe I'm going to explore, because I'm going to kind of make a guess here. I know that the normal force is the one that is kind of like between X and Y somewhere. So I'm probably going to use sines and or cosines, right, to deal with it in the component equations. I obviously neglected force of gravity because it's purely vertical when I'm looking at X direction, but there is a horizontal component, positive horizontal component of F sub n. So what should I do with that? I'm going to put a sine theta here. And what's my reasoning behind that? Well, we're looking for the ideal banking angle. What is the banking angle? In that sense, I haven't even addressed that really yet. But what makes sense is it's the amount that the turn is angled away from horizontal. So that's theta right there. And that thing is really the thing I'm trying to answer the question for, right? So it's got to come in somewhere. And then, okay, we're doing X direction. I think on the other side, we can just throw in mv squared over r. So I'm already jumping straight in. That's, I think, why I had that on the key concept slide, is pretty much any of these circular motion kind of problems. At some point, you're going to switch your MA out for an mv squared over r, but I'm still starting with F equals MA and doing the process. I just don't want to spend a lot of time worrying about that. Maybe I'm spending too much time talking about it right now. Do I need the Y components? Well, I think yes, because one of the problems is the normal force, no formula for it, so I'm going to have to deal with that in some way. So minus mg, I think, would naturally come in here, plus fn cosine theta. Oh, by the way, is anyone wondering, how did you know sine theta versus cosine theta? You know, we've done a number of these already. I mean, one thing we can definitely look at here is you could draw. I'm just going to draw an enlarged version of Fn here and maybe look at sort of a triangle associated with it. And I think it might make sense if that theta is right there. And then if this is really the x component there, and if this is the y component there, this maybe, I don't know if it's proper to label them that way. I should probably use subscripts, but whatever. Being a little lazy. But that means that x is opposite to theta. So that's one way of looking at it. But another way that you could also look at this is to recognize if the turn weren't banked at all, normal force would just point straight up. Cosine of 0 is 1 and sine of 0 is 0, which means it would disappear here and it would all be here, which is what would make sense. So that's kind of a quick little trick that I like to at some point share with everybody, a cool little kind of trick of the trade in that sense. Anyway, so let's go on and actually solve this here, because I think this y equation implies that the normal force would be equal to mg divided by cosine theta. And then if we plug that into the x equation, we get mg over cosine theta times sine theta is equal to mv squared over r. We can cancel those m's away. This is all a little weird looking, but sine theta over cosine theta is just tangent theta. So I'm going to reinterpret what I have there on the left side as g tangent theta is equal to v squared over r. And let me kind of go up here because I think I got some space still to work with. That means tangent theta is equal to v squared over g times r, dividing both sides by g. And so theta will be equal to the tangent inverse of v squared over gr. And I didn't write a list of numbers here, but at this point I think it's pretty straightforward to go and take the numbers given to me and put them in the appropriate places, because we're given a speed of 30 meters per second, so that'll go in for the v squared. And then for g, we know that it's equal to 9.81 meters per second squared. Oops, trying to make that kind of small in there. Meters per second squared, there it is. We're also going to need that 120 meters down there, so I'm running a little shy on space over here at the other end. Let me make that parenthesis a little bigger to match. So basically in your calculator, you're going to put in the tangent inverse of 30 squared divided by the quantity 9.81 times 120. I use parentheses in my calculator to put that all in line for the bottom part there. And in degree mode, my calculator spits out 37.398, etc. Maybe we can just round that off, in this case probably to 37.4 degrees as an answer here. And we can check it, and it's correct. I want to make a quick mention, though, before I close this video, as a little pitfall prevention. I went and worked this example out using all the tools that we're exploring in this class. However, the ideal banking angle is a very common topic in both textbooks, and there's a lot of resources online. And in that sense, if you put in a Google search for ideal banking angle, wouldn't you bet this formula pops up, because every textbook defines it in exactly the same way. The pitfall that I have, it's not necessarily that it's wrong to Google something. I mean, I think if you recognize, like, hey, I know where it comes from, but I also can just look it up and that's easier. There's nothing wrong with that. But the big pitfall that I've encountered with this is you have to recognize not every banked turn situation is an ideal banking angle situation. So make sure that if you look up this formula or even write this formula somewhere in a note sheet, maybe state somewhere that ideal banking angle, and maybe state if you are going to use this formula instead of deriving it based on the definition like I did, make sure that you state that this assumes no friction and no traction, because I've seen many times over on assignments and other kinds of assessments that people will use this formula because they had it maybe in some notes that I allowed or whatever, or depending on the exact conditions and how high stakes it was. But use this in a situation where there was actually friction or traction. You really needed to draw a free body diagram, go through the process to get the correct answer, but the person tried to shortcut it by either Googling or just writing from some notes this formula. So again, make a note. Don't do that. Make a note what the limitation of this ideal banking angle situation is, and therefore also this formula.